Greetings, everybody! Hey, we're going to talk about the formation and structure of stars now, which is a big topic, and this is chapter 9. We're going to try to scale it down a little bit so any normal human can feel comfortable with this material. Notice the beautiful image we have here on the screen right there. That's the Orion Nebula. This is a famous object, one of the real showpieces of the entire sky. We're looking here at an area of star birth because these kinds of thick hydrogen clouds also get cold inside of them, and so they're perfect for a cloud to collapse into something like a star. Let's dive in. Okay, star birth. They're born in molecular clouds. These things will have sometimes more than 1 million solar masses in them. There's lots of material. Not all of that coalesces into a cloud, into a star and planets. Most of it's driven off. The real issue here is about instability of the cloud. The clouds are big. They're usually light years across, and they're usually cold. And so the question is, can the gravity of the cloud, which is dependent on its mass, overcome the outward gas pressure, which is due to temperature? Here's the thing you have to keep in mind. The gravity always is trying to collapse everything. Gravity is an attractive force. Its job is to try to make everything smaller, including clouds. And the pressure is just the opposite. It's a natural opposer to gravity. The temperature, the higher the temperature is, the greater the pressure will be. And so these two, the pressure is an outward force, the gravity is an inward force, and these two are constantly at war with each other. And if the gravity doesn't win out, you won't get star birth. So sometimes it requires a trigger. In other words, the cloud has to get hit by a supernova shock, or a collision with another cloud can actually do the same thing too. Another thing to keep in mind is that all clouds, in fact, all big things in the universe, including the Earth, which is not really that much of a big thing, are spinning. And so this spinning, believe it or not, has a very powerful effect on clouds. They tend to form disks instead of just falling into a spherical star. The disks form because the cloud is spinning, and I'll tell you a little bit more about that in a minute. The really big clouds cannot form super huge stars. Now, there is a reason we don't have a lot of stars that have 200 solar masses or something crazy like that, is because the stars actually get hot. And so they simply fragment into much smaller clouds of like 10, 20, or 30 solar masses. Even those are quite large. Okay, here's the kind of HR diagram that I like because it's really transparent what's going on. Remember, here's the definition of an HR diagram. We're plotting luminosity, and in this case, it's in solar luminosities, which is the best kind. And we also are plotting in the x-axis temperature. This is surface temperature for these objects. And remember, the funny thing about these numbers is that they are increasing to the left. You guessed it. Yeah, they are not increasing to the right. That's because the astronomers that set this up 100 years ago liked the sort of patterns they saw when the numbers are going to the left. So they just decided to use it. It's that simple. Now here's the main sequence. Notice it says 0H main sequence. This is, remember, everybody on the main sequence is doing what? Burning hydrogen for a living, okay, in their cores. That's an important point. The stars way up here in the upper left are the massive big stars. The stars way down here on the right are the small stars that barely can pump their cores up to 10 million degrees. Remember, that's the ticket of admission to becoming a star. Whereas these guys, geez, 100 solar mass star, wake me up at 3 in the morning if I'm a 100 solar mass star, and I'll pump my core up to well beyond 10 million degrees, and they do. This is showing you, however, how stars are born. These are the tracks of star birth on the HR diagram. They're coming pretty much from left to right, although some of these are vertically downward. Notice the 100 solar mass star gets to the main sequence in 10,000 years. That sounds like a lot. But take a look at these guys. The 0.1 solar mass stars, these are about as small as they get, take 100 million years to get to the main sequence. So there's a big difference of opinion among stars about how long it takes to get to the main sequence. Now, and sun-like stars, you can see it right here. There's a 1 solar mass star. This is the track. And then just between 1 million and 10 million years, it comes in and hits the main sequence. This is just giving you a few little facts about what it takes to collapse towards stardom, meaning burning hydrogen. Protostars, that's the word for stars that are not, for clouds that are not hot enough yet to burn hydrogen. The protostars are usually surrounded by some sort of a nebula, so we can't see them very well. And why is that, you ask? Because remember, the protostars are born in gas clouds, or also called nebulas. So it's natural for them to be surrounded by them. At some point, they cross the birth line on the way to the main sequence, and they become what are called young stellar objects. There are other names for them too. And the birth line simply means that this cloud is blown away as this protostar gets brighter and brighter and brighter. This is when disk formation occurs, protostellar disks. These are the disks that become protoplanetary disks, because this is where planets come from too. Remember, the disks form in the plane perpendicular to the rotation axis of the cloud, if you think about that for a second. And that's simply because the cloud is collapsing like a pancake. It can't collapse in the plane perpendicular to the rotation axis because there's too much centrifugal force due to the spin that's actually opposing it. So you get protostellar disks very frequently. T-Tauri stars are just a particular type of star that people see after the birth line. About half of the T-Tauri stars have disks associated with them. Here's a diagram showing you what they look like. On the way to becoming a star, the central area is getting very hot, but it's not quite hot enough yet to burn hydrogen. But notice all these interesting disks in the same plane. The actual rotation axis would be coming out of the screen at us here. Okay, now here's a super important idea for you. The idea of, excuse me, stability of stars. The term that's used in the text, of course, is hydrostatic equilibrium. That simply means, is the star stable or not? Remember, we got two forces, pressure pushing outward, gravity pulling inward. And so when these two are in balance, you have equilibrium. In other words, there's no great expansion, there's no great collapse. The star is truly stable. Here you can actually see what happens at each point inside a star. We have the gravity versus the pressure, and as we go deeper, notice the gravity and the pressure gets larger, and finally near the center, the gravity and the pressure get very large, but they're always, you guessed it, equal. Now, why do the pressure and gravity get larger towards the center? This is because of the gravity that's pulling everything in towards the center. It's like having, you can think of these layers as like stacks of books. If you're way out here, it's like having maybe 2 or 3 books in your stack. They don't weigh much, so the gravity is not very strong, and it doesn't take much pressure to oppose it. But when you get in towards the center, it's like having a big stack of books that's hard to pick up. That means the gravity is very strong, and so to keep stability, the pressure also has to be strong. Now, the pressure and the temperature, by the way, are related. They go together. So whenever the pressure is high, the temperature gets very high. And there's the secret reason, friends, for why the temperatures in big stars are very high. Because there are a lot of layers, a lot of stacks of books pressing down on the core, raising the pressure, which raises the temperature up to millions of degrees. If you can't get your temperature above 10 million degrees, remember, you can't be a star. You become a brown dwarf or something like that. Oh, here's the basic idea. When the pressure is greater than the gravity, pressure is outward, remember, gravity is inward. When the pressure, the outward force, is greater than the inward force, you get expansion of the object. And that happens too. We'll talk about that in the next chapter. Now, when the gravity is greater than the pressure, you get collapse. Okay, that's what we're talking about right here. Now, 3 ways energy is transported. Conduction, convection, radiation. This isn't just in stars, this is anywhere. Conduction means heat moves from atom to atom. Generally, this is the slowest thing. It's like, I'm trying to think of an example here. If you pick up a warm hamburger, the heat from the hamburger will be conducted from the hamburger into your hand. That's conduction, okay? Likewise, if you pick up an ice cube, the heat from your hand will be conducted into the ice cube and probably starting to make it melt. Convection is like boiling water. It's when the either the fluid or the gas, whatever it is actually moving in circulation, and the heat is being carried literally by the motion of the water. And boiling water is a classic example. When you put a pan of water on a stove, what happens is the pan gets warm, then the bottom of the water in the pan gets warm, and then you set up a circulation so that that heat from the bottom of the water gets transferred to the top. By the way, this is the way the outer layer of the sun works. Remember, there's a conductive layer there. Now, radiation requires, unfortunately, we cut it off for you here, but radiation requires a transparent medium because you can't radiate in an opaque medium. And so that's the primary. Radiation is a great way to move energy around, but it needs to be in a transparent medium. Oh, here's an important misconception, common. I think it's very common. That's on page 190. You should check this one out. It's really important to have this straight. The sun's, a lot of people think, and this is wrong, friends, that the sun's core is hot because nuclear reactions occur there. Nothing could be more untrue. It's the reverse. Okay, nuclear reactions occur in the core because the sun's core is hot. Okay, remember to do nukes in the core, you have to be above 10 million degrees. And if you aren't above 10 million degrees, you're not going to have any nuclear reactions there. You won't be able to burn hydrogen into helium and give off energy. So the statement's backwards. In fact, the sun and other stars have nuclear reactions in their cores because it's hot enough to do it there. And they have to pump up themselves, their core, above 10 million, or they won't be able to have nuclear reactions. At least 10 million degrees. There you go. Okay, this is a great little figure out of the text that I like, so I wanted you to take a look at it with me here. This really gives you the spirit of how this all works. That is, making computer models of stars. This one's of the sun, because you can see there's one solar mass right there. But you have somebody, these are actual real equations called the equations of stellar structure. They govern things like how mass and luminosity and temperature and pressure vary with depth in the star and so forth. That's coded into a computer, and then they put constraints on it, like what is the actual mass of the sun, what is the actual radius of the sun, what is the actual temperature, and so forth. And you come out with a bunch of numbers. It doesn't look that exciting this way, but this is how it's actually done. Over here, we've got the radius. Here's the center. Here's the surface. Notice right away the temperature near the surface is low, but when you get into the center of the sun, notice it's almost 16 million degrees. Here we are about somewhere around 15% of the way out from the center of the sun. We hit the magic 10 million degree number where we can burn hydrogen. The other thing that's fun here is notice the density. The density at the center of the sun is 150 times that of water, because 1 gram per cubic centimeter is the density of water. So to give you perspective on this, a typical density of a surface rock, like say a granite, which are very common surface rocks in mountainous areas, have densities of about 3 times that of water. So 3 into 150 is 50, I think. Yes, it is. And so what that means is the density of the center of the sun is 50 times greater than a typical granitic rock. And the thing you have to remember is the sun is completely a gas. So how can something with 50 times the density of a surface rock like granite be a gas, you ask? I'm glad you asked that. And the answer is right over here. The temperature is almost 16 million degrees. So this is an extreme environment, to say the least, inside the sun. And only with these humongously high temperatures can you have real high densities and still have a gas. And then you could actually see, here's the outer convective layer I was talking about. Inside the sun, there's a large radiative area because it's transparent, and energy moves out of there. An individual photon, remember, might take 300,000 years to get out, even though the light time is just over 2 seconds. But that was an interesting thing we talked about before. Okay, now in this chapter, he ends up by talking about main sequence stars. These are sort of the fun facts you need to keep in mind about those. All main sequence stars burn hydrogen in their cores. That means they must be above 10 million. This is the mass range for typical main sequence stars. Nothing smaller than 0.08, just under a 10% of MS is the mass of the sun. To in excess of 30 solar masses, there are very few stars above 30 or 40 solar masses. But that's a typical range. The lifetimes of these things vary with the mass, okay? The lifetime of the sun is 10 billion years. That means the sun will be on the main sequence burning hydrogen for, you guessed it, 10 billion years. If you have a very large mass, this is mass to the 2.5 power. So the lifetime of the star is simply 1 over the mass of the star in solar masses to the 2.5 power. Okay, so what that means is that as the masses get big, the lifetimes get very short. And you'll see that in numbers in 2 seconds. The zero-age main sequence is where the star ends up after this long pre-main sequence track. This is where it begins burning hydrogen, but it doesn't stay there long because sun-like stars, for example, increase their luminosity, that's the energy per second being coming off the star, by 10% per billion years. That's what's been cut off here. So the luminosity actually increases by 10% per billion years. That's a lot. Now, this is a table out of your text. Unfortunately, I cut off some of it with my picture here, but this reminds you of spectral types. Over here, you should know what these are, OBA, FGKM. You should know the O's are the hots, the M's are the cools, and the G's are like the sun. And this is giving you mass ranges roughly. So notice the O stars are humongous, 40 solar masses. Give me a break. And the B's can be large too. Obviously, since you only have to be above 8 solar masses to go supernova, these kind of stars are going to blow up at the end of their life, which, by the way, won't be very long. Because notice the big O stars only hang around for 1 million years on the main sequence. That's almost nothing. And even the big B stars are around for about only 10 million years, okay, which is almost nothing. Notice the luminosities here. Actually, the luminosity of the biggest stars goes up to like 1 million solar luminosities. It's mind-boggling. Down here, the M stars have masses in the 0.5 sun angle, and these guys will live for like 60 billion years, although I cut it off. You can check this, it's table 9.1 in the text. So even though these are small stars, the reason they live so long, and by the way, some of these red dwarfs down here can live for trillions of years, not just hundreds of billions of years, which brings up an interesting point, and that is that none of the red dwarfs that are alive now will ever die. Well, let's put it differently. Any of the red dwarfs that are alive now in the entire universe, all of the ones that are alive now, none of them have ever died because their lifetime is longer than the age of the universe. Remember, the universe's age is only 14 billion years, and typical red dwarf will live 50, 60, or several hundreds of billions and sometimes into the trillions of years. That's just the way the universe works.